Yeah, so last time what we did is we looked at, the main thing we did is we looked at kcat over km as a specificity constant. Okay? And we saw that kcat over km, I'm not going to write anything down right now because it's in the notes. We saw that kcat over km times E times free S was equal to velocity under all conditions, and that we could divide that for substrate A and substrate B. If they were equal concentrations, they would cancel out. If the enzyme was in the same tube, it would cancel out. And so that we could think of the relative kcat over km's as the relative velocities when you have two competing substrates in a tube or in a cell with the same concentration of enzyme. And then we looked at different limiting conditions. We looked at kcat over km. We know km is equal to k2 plus k minus 1 over k1, and we considered where k2 is faster than k minus 1 or k2 is slower than k minus 1. And we saw conditions where the rate was limited by binding or where it was in rapid equilibrium. And we drew free energy diagrams for those. So maybe by way of review, what would be good to do would be to look at a couple of those and then go from there. So, all right. So let's take, these are kcat over km. And we're going to let this be k2. And we know that this is k2 plus k minus 1 over k1. And remember, we saw two limits. One was where k2 was small compared to k minus 1, and the other was where the opposite was true. And so if you look at the math, we know that if k2 is small compared to k minus 1, that here, that kcat over km is equal to, I'm running out of space, is going to equal to k1, k2 over k minus 1. And that here, kcat over km was going to equal k1, right? All right. So let's do this. Let's go ahead and plot those just for practice. And so remember, we said that this is some kind of activation energy versus reaction. And so we have to start out, and we have an initial state. Remember, this is E plus S. And we know that all the reactions go uphill, like that. And that, in this case, because k minus 1 is faster, when it goes to k2, it has to go uphill. And then it comes down like that. So this is ES, and this is E plus P. And here, also uphill, we get to the top, we come down, but now we do this. Because k2 is faster than k minus 1. Anybody have questions on this? It's really important to understand these. Really, really important, I think. Because a lot of times when I'm trying to think about I mean, Erica and I were just sitting down for the last hour or so or more, going through various kinetic scenarios, and there's always different ways to think about things. And one is to write down reaction mechanisms, and that's a real classic way of doing it. You know, as you guys know, the reaction mechanism that we're using here is this. But the other is to use these energy profiles. And then another is to do simulations, and that's what we were starting to do. And I'd like to find a time to do that with you guys too and show you some simulation programs and where they come from using numerical integration. But you start out with this state, E plus S, and then you go to the next state, ES, and then you go to the final state, E plus P. And here I know K2 is faster because if K2 is faster, that means it's got a lower barrier. And this is the barrier for K2. And you can see that that barrier is lower than the barrier backwards for K minus 1. And then you can see that this is the transition state. So once I get over that mountain, it's all downhill from there. And that's why K1, which is this process, is rate limiting. And then over in this guy, it's the second mountain that's rate limiting. And so it's in rapid equilibrium across this guy, which is why both K1 and K minus 1 kind of show in. Okay. Any questions? So this whole page is under conditions where the substrate concentration is less than Km. In other words, these are subsaturating. When you raise the concentration of substrate so that it saturates the enzyme, effectively what you do is you raise this barrier right here. So let's go ahead and do that on the next page. So now I'll try and write a little neater. And it turns out that that same set of equations holds because Kcat over Km is the second order rate constant between free enzyme and free substrate, and that holds under all conditions, not just Kcat over Km conditions, because of the way it's derived. So we can go ahead and plot the data. And again, this is a reaction energy. This is a reaction coordinate, or you can think of it as reaction progress. Bond making and breaking. And so let's do in the same order that we did on the last one. So let's have K minus 1 be fast first. And so what we just wrote back on this page for this condition, when K minus 1 is fast, it looks like the top one here. So when K minus 1 is fast, it should be like that. So that is where S is, sorry, that's still S less than Km. And so now when we raise the concentration of S, effectively what we do is we raise that. Okay. So now that's S greater than Km. So you just raise the E plus S state. ES is not affected and E plus P is not affected. Or in other words, if you want to just draw it alone by itself, where S is greater than Km, it looks like this. So effectively, the reaction is starting from here, from the ES complex, and going to E plus P. So it's really, what you're measuring is the reaction of the ES complex. Whereas over here, when the substrate concentration is low, you're measuring the reaction from E plus S to E plus P. They're two really different things. And you could do similar sorts of diagrams for the other case where the on rate is rate limiting, but I think I'll just do this one. So why is this the case? Let's talk about pseudo first order rate equations. So just to remind you, you know what a real first order is. I've been emailing back and forth with these Doceri people about this flashing, and they said they'd never seen it before. And they had me doing all sorts of things to my computer, all of which I've done, and hasn't made it go away. They gave me one last heroic thing to do, which I haven't had the time to do. To uninstall my Java, uninstall the program, reinstall everything. I'm like, oh. All right. So real first order is just A goes to B. Let's have it a rate constant K1. And real second order is A plus B goes to C. You know what? Let's do this. Sorry, let's make it P in both cases, so that we don't have B being a reactant in one case and a product in another. Let's just do this. All right. So we know how to write down the rate law just by inspection. Let's put K2 in here. So pseudo first order means that it looks like it's first order, but it's not. And so you take a second order rate process like the one on the right, and you make it appear like the one on the left. And the way you do that is you let something be in excess. Okay? So what do you guys want, A or B? B. So that's fine. So now we know that as we do the reaction, the concentration at B is hardly going to change at all, even if all A is used up. Does that make sense? So B is a constant. And a constant times a constant is a constant. So I'll go ahead and write it out first time through. I'm going to rewrite the order. These two guys are constants. And so we'll just put them in as another constant. I'll call it K2 prime. And it acts like a constant, but it's not really constant. So it's pseudo constant. If I change the concentration of B, then I change K2 prime. And so it's not really a constant. K2 is a real constant. If I change the concentration of B, the value of K2 doesn't change. So that's why it's called a pseudo constant. So why do that? Well, it turns out that it's easy to handle the math on first order equations. And so one of the tricks to handling really complex data sets is to hold something constant throughout a reaction, do a set of reactions, and then change it to a new value, hold it constant at that new value, and redo the experiment. So I like to say then it's parametric in the concentration of B. But let's go back to the first order and see why it's simple to handle this. So the velocity is dA dt, right? Minus dA dt. And so it's really easy to integrate this. hopefully everybody knows how to do this. So you just go from t equals 0 to some time t. And at t equals 0, the concentration of A is A naught. And at some later time, it's the concentration of A. And so it's minus the natural log of A, evaluated from A naught to A, equals K1 times T, evaluated from T to 0. And so this is just equal to you all know how to do this, I'm sure. So then you end up with A over A naught. And you can stop there. You can just say that that's equal to the fraction of A. That's what we like to do in our lab. But some people just, will do this. And plot this as A versus T. And that value is A naught. Or you can do what our lab likes to do and just say that this is fraction of A. And then you can plot fraction of A versus T. And that will go from 1 to 0. And you can fit that. You can linearize that if you want. I wouldn't do it. I mean, I already have it linearized down here. It's already linearized here. So if you wanted to, you could plot the natural log of A versus time, and the slope would be minus K1. But no one does it that way. Well, some people do, but most people don't. They'll use nonlinear regression. We like to use kaleidograph, but there's lots of other origin, Igor, Pro. There's lots of programs to do that in. Okay, and so your data, I didn't actually draw data, but you take time points, and if you're lucky, your data is kind of scattered evenly about the line, and you fit it, and you get out your K. Okay, so that's true first order kinetics. Okay, pseudo first order, you can do the same thing, because this equation here try that again, is equivalent mathematically to that equation up there, right? It's just that K1 is now equal to K2 prime. And so, so once you do that, you can then change the concentration of B, and then you can plot K2 prime versus the concentration of B, because you know that K2 prime is equal to K2 times the concentration of B, right? You guys can see that right here. And so you pull out K2 prime from these exponential decays, then you redo the experiment at a new concentration of B, and you plot K2 prime versus the concentration of B, and each of these is at a different concentration of B, and then the slope of this line is what? K2, what you're really interested in. So that's how I would go after a second order rate constant, is to turn it into a first order rate constant by holding B's concentration in excess doing an experiment, changing it again and again and again. So kind of my rule of thumb is that I've drawn some data points in there, but I'd say 5 for publication. Minimum number of points on a straight line, kind of rule of thumb, is 5. More is always good. Minimum number of points in an exponential decay is at least 7 or 9. If it's a double exponential, you need more, 10, 15, 12, 15 points. Okay? Does it make sense? I think that's all I wanted to say. So that's what pseudo first order is. Now if I go back one slide to this one, let me write the mechanism under here again. I'm going to try and write small. We all know this mechanism. What can I do with what can I do with S? So this guy's bimolecular, right? But I can make it pseudo first order, because we know that the rate for that is K1 times E times S, right? But S is an excess, and so the pseudo first order rate constant for going across here is not really K1. I could write this as K1S with just E going across. So it's totally okay to do this. Where now I have this pseudo first order constant, which is the true second order constant times the concentration of S. And we know that's not a true constant because S can change, but I'm holding it constant and in excess for my experiment. And if that doesn't totally make sense, if I go forward one slide and go back over to here, we can always work backwards, and we did this with the kcat over km specificity. So I can go in here, and if I see this, I can think that this is A goes to P, right? Because that's what a first order process would look like. So what I can think is A goes to P, because that's what for that type of mechanism, that's what the rate law would look like, and it would go at a rate constant of K2 prime. But we know that K2 prime is simply equal to K2 times B. Okay, so that's kind of what you can think. That's a thought cloud. You know how they have, like in cartoons, people thinking, and they show those clouds? I didn't do a very good job on that one. They're more spiky. That's what you can think. Okay, so you bimolecular, you can think about it as unimolecular, where the rate constant is the true rate constant times the concentration. So we go back here. That's what I did down in this corner with the purple box. So now it looks like a coupled set of unimolecular processes. We don't have to worry about the E plus P. It can't really go backwards because the concentration of P is really low, at least under initial rate conditions. And so now, when we go back up here, and I told you guys that here that when you raise the concentration of S, what you do is effectively just raise the ground state. That's because you're effectively increasing that rate constant, because that rate constant is just K1 times S. And so that's where that comes from. Okay. All right. Pretty nice, huh? Okay. And I did competing, last time I did a few competing substrate profiles. I could do some more, or I could do kinetic shortcuts. What's your poison? More profiles or shortcuts? Shortcuts? Okay, let's do some shortcuts. Maybe the Quizlet form would be good for reviewing some of those. I have some more examples, but let's do something new. So they come from this guy, W.W. Cleland. He's passed away recently. He was at the Enzyme Institute at the University of Wisconsin. People called him Mo Cleland. I met him twice in my life. Once I invited him when I was a grad student as a student-invited speaker, and another time when I was an assistant professor. I went out to University of Wisconsin. I gave a talk. He's like a giant of a man. I mean, really big, like 6'3", 6'4", and also just very, like, really big person, but really super nice guy, and incredibly smart, and written like lots of classic papers on enzyme kinetics, multiple turnover, inhibition, and a lot of heavy atom isotope effects, like those of you who know Mike Harris's work and ribozymes. A lot of that goes back to Mo Cleland. So that's the person who I'm aware of who came up with this. So, all right, so why do we need this? Well, we know when we write this down that this is not everything that's going down, right? I'm going to write this as, well, how do I, let's keep it as K2. That's what we've been using. Okay. We know that's oversimplified. And be mindful, too, back on the last couple slides where we did pseudo first order, that those only hold under certain conditions. Those only hold when the substrate is in excess or B is in excess. That's not always the case. Okay. All right. So, but we know that there's a EP, and then that EP dissociates to give E plus P. So once we make the Michaelis complex ES, there's chemistry that happens. That's the chemical step right there. And then EP forms, and then the product has to dissociate. All right, so let's go ahead and give each of these constants a name. And we'll just use our systematic notation. And the question is, how do we handle that? It's starting to look pretty hairy. One thing is we can just punt and go to simulations, and I'll show you next time how to do that. But sometimes there's a certain, I don't know, elegance in terms of handling the math and figuring out how to handle the math. And so the first thing that I do when I look at something like this is I have to make one of the reversible constants go away in order to simplify it. And I'm going to make k minus 3 go away. And how do we make k minus 3 go away? Well, we know that that the rate for that process right there is equal to V times E times P times K minus 3. Usually I write the K minus 3 in front. But just write down the rate law, right? And so during initial rates, not much product has formed yet. So that rate's going to be super slow. So under initial rate conditions, we're just going to not draw K minus 3 in, essentially, because that reverse rate is so slow. And that also is an assumption. So I'll go ahead and write everything over one more time. And I haven't done any funny business yet with the rate constants. I'm about to. But these are still K1, K minus 1, K2, K minus 2, K3. Okay. So what we're going to do is we're going to play a game. And we're going to make K minus 2 disappear. We're going to turn this into a set of effectively irreversible rate constants, and then we'll go back and we'll fix it. Okay. So this is this is K3, but this is no longer K2 because I messed with it, so I'll call it K2 prime. This is still K1, and this is still K minus 1. And so the question is, what is K2 prime equal to? Okay. Well, it's the best way to write this out. Probably over here. K2 prime is equal to the real K2 times the partitioning factor. And the partitioning factor is the likelihood of once we advance from from ES to EP, what's the likelihood that EP is going to go forward versus going back? That's its only two choices. If you're EP, you can go forward at a rate constant K3, or you can go back at K minus 2. And so the partitioning to go forward is K3, over K3 plus K minus 2. Okay, and it almost might be better if I wrote this, same math, but if I just wrote it a little bit differently. Like that. So in other words, K2 prime is equal to K2 times the likelihood of going forward. And you can see that that term I put in parentheses could never be bigger than 1 because of the way it's written. Those numbers are positive. So it's a number divided by the same number plus something else. So the biggest it could be is 1. It could be less than 1. And that's what K2 prime is. Okay, so this is where the shortcuts come from. So now we're going to get rid of K minus 1. And we'll call that K1 prime. And K1 prime is going to be equal to, well, now what we're dealing with is we're looking at ES, and it's the likelihood that ES is going to go forward versus go backwards. And so ES can go forward at a rate constant of K2 prime, not K2, but K2 prime. divided by the sum of these two. Oh, sorry, I messed up here. So it's K1. This should be K1. So it's K1 times now the partitioning for ES, and that's K2 prime over the sum of K2 prime and K minus 1. And then once you have all this, let me shrink this down. You can actually just say that E plus S goes to E plus P. So it's essentially a first order, pseudo first order of S going to P at K obs. And now, because it's a set of irreversible ray constants, if you think of it as adding, you think of it like a circuit. So if you guys are familiar with like electrical circuits, and you have a bunch of resistors in series like this, then you add them as the inverse. So actually you add sort of the flow, like it's flowing through pipes. And so if each of these guys is a different pipe, and the narrowest pipe is what slows everything down. So these are in inverse time, but if you take their reciprocals, they're in time. And so you basically say that K obs 1 over K obs is equal to the sum of 1 over K1 prime plus 1 over K2 prime plus 1 over K3. And you're done. Okay? So that is how you handle it. Now you can go through and, if you want, you can do all the math. And in order to do that, I'm going to go on to the next page. And then we'll stop. It's actually pretty easy. So, what's the easiest way to do this? The first thing is to, so I would say that these are sort of parametric equations. They're kind of defined in terms of each other, but we can go first to the second equation, this guy, K1 prime, and this equation. And we can substitute in. And I think the, well, let's go ahead and just see what kind of trouble we get ourselves into. It might be easier to do them, it might be easier to leave them upside down. So in other words, for this equation, go 1 over K1 prime equals K2 prime plus K minus 1 over K1, K2. Hold on, I did this earlier. Let me see if I can find my notes. Here it is. Okay, I did it similar to this, but let me do it the way I did it in my notes. Okay, so what I did is I just worked from the last. I worked from this equation. Okay, and so and I left the 1 over k3. And then in place of the 1 over k2 prime, I took the upper one and inverted it, k minus 2 plus k3 over k2 k3. And then, I'm writing too big. Okay, so in other words, that takes care of that, this takes care of this, and then for 1 over k1 prime, I'll have k1, and then I have k2, I'm flipping it, I have k2 prime, 1 over k2 prime, or I just have k2 prime, and k2 prime is equal to k2, k3 over k minus 2 plus k3. And then in the numerator, I have k2 prime plus k minus 1. So I have that. And anyhow, you can keep going, and what you'll end up with is that what you do is you have to get, I'm not going to do all this because it's boring and it's better if you do it yourself, but here's the steps. Is you make a common denominator, and if you go back, you can see that that common denominator, if you look at this, you can see that these two guys are going to flip up on top, and your common denominator is going to be k1, k2, k3. And so you're going to multiply this by k1 over k1, and you're going to multiply this by k1, k2 over k1, k2, and you're going to get a common denominator of k1, k2, k3. Okay? And then once you have that, you're going to flip the whole thing back over, because once you get that, it's still 1 over k obs, so k1, k2, k3 is going to go up into the numerator, and it's going to end up looking like this. Oh my God. Yep, that's what it looks like. Okay, and if you're under pseudo first order conditions where the concentration of S is much, much greater than the concentration of E, then you can use K1 prime equals K1 times S. So wherever you have K1, you can put in, I'm not even sure I should call it K1 prime. Right? Just K1 effectively becomes K1S. And so it's really equal to K1S, K2, K3 over, and then you have to go all the way through. And wherever you see K1, replace it with K1S. And while it looks ugly, it's really not that bad. And you can do, so what you'll see if you go in and you look at some of these older papers, or not even older papers, you'll see values for Vmax and Km in terms of all of these. And so you can look at this and say, well, how does this compare to V over E naught, which is K2 times S over Km plus S. And you can ask, where is Vmax and where is Km in all of this? And I went through and did that. And I don't know whether you guys want to see that or not, but basically you can factor out S in the denominator and then divide through by that constant, and then that will allow you to get a true Km out of it. I'll just show you real quick. So you take S and you factor out K1, K2, K3 times S, and then you can see here there's never any coefficient multiplying S, and so you can't have one in this either. And so the way you do that is you first factor out S. Sorry. Okay, like that. And then you have your other three terms still left over here. And so when you do this, just to see what Km is, Km is equal to this piece here divided by that piece, because you'll need to divide top and bottom in order to isolate S, and that's how you can get Km out. Make sure I did that right. Yeah. So Km is equal to this guy divided by that guy. I don't feel like writing it all out. But people will go through and basically approach the problem like this, use the kinetic shortcut, set it up, compare it to the way you plot the data normally, remove the coefficient in front of S, and be able to pull out Km in terms of all the rate constants that way. Okay. So I don't really use this very often in our research, but occasionally we do. And just quick, and then then we'll stop. So this is kinetic shortcuts. You write down everything you can think of, get rid of the last step, and then start replacing reversible steps with irreversible steps, in which you use this partitioning going forward. Use primes, invert everything, add them up like resistors, flip them, do the math, add them up with a common denominator while they're inverted, flip them back over, and then compare them to the standard Michaelis-Menten. It's just algebra. You guys can all do it. It's not difficult. So since Erica and I were doing simulations, I think maybe next time we get together, and I think maybe next week, I'm pretty sure next week's okay for me, maybe we can do simulations. And maybe in the meantime, well, maybe not, it's summertime. So maybe what I'll do is I'll bring a program. It's free. We found you could download it. If you guys want to, maybe interim, I'll send you the link. You could download it. But it'll be a lot easier if you let me show you how to use it. And it's really nice because you can put in a mechanism like the one at the top or the one below it, or one even more complicated than that. And you can put in guesses at your rate constants, you can put in guesses at your substrate, and then you can just see what the plots would look like. And you can have it export data too. And you can even put in your own data if you buy the full version and fit your own data, and you can fit it globally. So this is Ken Johnson's program. But the program costs $1,000 if you want to be able to fit your own data. So we're going to take the plunge. We haven't yet. But Ken is an old friend of mine, and so he does things right. He's a brilliant kineticist. And a lot of the labs here use it. Marty Bollinger's lab has 3 of the keys. They use it. Does Dave, do you guys use it in David's lab?
Not that I'm aware of.
You could be the first one. We could get one, you can come use ours. I shouldn't record that. But
And then convince Dave to get his own.
yes.